Great. Today we are going to start discussing some special functions. We're going to start with absolute value functions. So if you notice, all the way to the left on the grid, I've pre-plotted the parent function f of x equals absolute value of x. As you'll notice, it's got a classic V shape with the vertex, or in other words, the place where the curve changes direction is called the vertex. That's at the origin of 0, 0. So what I want to do is use the next 4 examples to demonstrate how you can alter or translate these absolute value functions from the parent function. And it would be very helpful if you had a notebook, because I'm going to talk about horizontal translations first, so moving the basic parent function left and right. Then I'm going to throw in an example that includes a horizontal translation and a vertical translation, meaning up or down. And then I'm going to show you a translation that kind of puts all things together, including stretching or contracting the parent function and also flipping it over. So let's go ahead and use different colors to represent these different things. So for the first one, I'm going to use a blue color, and I'm going to show you what absolute value of x plus 2 is. So in order to do this, I want you to notice that we're doing something inside of those brackets, those vertical brackets, and we're adding something inside of the function. And again, I'm using the word inside very carefully. What it always does, whether it's absolute value functions or parabolas or what have you, it's always going to move the parent function, the basic shape of it, to the left by that amount. So the vertex here would shift from 0, 0 to 0, minus 2. So that would be about right there. And then the rest of the function would look exactly the same. It would be a V shape going this way and going to the left. Okay, so that's the first one. It's a horizontal translation to the left, and to make something go to the left, you have to add something inside the function. It sounds counterintuitive, but that's the way it works, so make sure you memorize it. Okay, so obviously if you're adding something inside of it, now that you know that it moves it to the left, subtracting something would move that to the right. So I'm going to use green to show that. So I'm going to do absolute value of x minus 3, which means I'm going to move to the right by 3, and then it's going to be the same shape. So 1, 2, 3, and now I extend this, and I extend that. Okay, and that's your absolute value of x minus 3. All right, so going on to the fourth example, absolute value of x minus 3 minus 2. So you know absolute value of x minus 3 shifts the parent function to the right by 3. Then the minus 2 will actually move it down by 2. So I'm going to use kind of like a purplish color to illustrate that. So I'm going to start with where I was, and I'm going to move down 2. And then I'm going to draw in this function again in this purplish pinkish color. Okay, so there you have it. That's absolute value of x minus 3 minus 2. All right, so finally, this is the one that's going to be the most complicated example. I've got absolute value of minus 2 times the absolute value of x plus 2 minus 3. So we're going to do things in an order of operations type of manner. All right. So remember that f of x is really kind of the same thing as y. It really is. So what this is going to do is it's going to move the parent function to the left by 2, and then it's going to move it down by 3. Okay, so off to the left by 2, down by 3 puts us about right here for a point. Okay, now the 2, let's just talk about the 2 before we talk about the minus. The 2 basically multiplies everything, okay, that's produced inside the function by 2. So if you imagine that you had the value of 1 for x, okay, it would make this function evaluate to 1 plus 2, which is 3. Okay, absolute value of 3 is 3. Then if you multiply it by 2, that makes it 6. So what you're really doing is you're creating a much bigger y value than you would if the value was 1. Because if the value was 1 in front of all of that, it would just be absolute value of 3 times 1 is 3. But if you're multiplying it by 2, it's 6. If you multiply it by 3, it's 9. And it just produces a bigger y value. So the effect of that is to create a steeper set of lines, okay, or branches, and therefore a narrower curve. Okay, so that's what that does. Now, what about the minus? Well, the minus basically takes something that was positive and flips it over, right? It makes it minus. So instead of minus 6, instead of 6 for y, you would have minus 6. You understand? So it just completely flips over the curve effectively, and the curve would look more like this. It would start at that vertex of minus 2, minus 3, and it would go down like this, and it would be narrower. Okay, so that light blue line shows you how that works. What I'd like you to do is make sure you understand this, memorize it, and if you really want to get some hands-on learning, I suggest you take each one of these functions the way I've written them, and then create a table of values where you're using both positive and negative x values, evaluate them, create the table of values, plot them, and see for yourself the effect of all these different transformations to kind of prove it to yourself. Does that make sense? I hope so. Now we're going to talk about piecewise functions. Okay, piecewise functions are described taking on different values of f of x, or in other words, y, and they'll take on different values depending on the domain range of x. So let's use some practical examples, like the first one that I have, which is f of x is equal to x plus 2, which if you were to convert that into like y equals x plus 2, you'll notice that y equals x plus 2 is just a simple linear equation. It's a line of slope 1 with a y-intercept of 2. So if you think of this as y equals x plus 2, whenever x is greater than or equal to 2, and this is a key, we're giving a domain here of x greater than or equal to 2. So from 2 and on to the right, it takes on the value of x plus 2, or a line that looks like that. Now, if we have, and now the second part of it is, this function takes on the value of minus x whenever x is less than 2. Okay? So now if you convert that into y equals minus x, you'll notice that that's, again, a simple linear equation. It's just a negative sloping line, okay, of slope 1, or I should say of slope negative 1, and that's for all values of x less than 2, okay? Now notice that we have an x greater than or equal to 2 and an x less than 2. Whenever we have greater than or equal, we use a closed circle to represent that, okay? And whenever we have a value that's just either less than or greater than with no equals, then we use an open circle, because effectively it means that the value can get really, really close to that number, but it can't actually be that number. I hope that wasn't too confusing. You might need to think about that, a couple of times. Okay, so now let's look at this. F of x equals x plus 2 for x greater than or equal to 2. So let's look at the value of x equals 2. So x equals 2 is 2 units to the right of the origin, and then if x is equal to 2, then that value will be x plus 2, or 4. So we would have a value at 2, 1, 2, 3, 4 up, okay, and then it would be basically a line that looks like this, going off to the right, okay, and we would also have a small closed circle at 2, and I'm having a hard time drawing a closed circle. Okay, now the other part of it, minus x for x less than 2. Okay, so what we'll want to do is draw that maybe like with a little bit different color, like a blue. Okay, so at let's say at x equals 2, you get minus 2 for y. So that would mean that at x equals 2, a minus 2 would be down here. So it would start down here, and then it would go off to the left with a slope of negative 1. Okay, and here at that point, we would have a open circle like that. Okay, and this other one up here was supposed to be a closed circle. So you can see that this function takes on different values within different domain ranges. Okay, that's really the best way to describe these piecewise functions. Now, there's also something else interesting about them. Okay, and I'm going to show you how you can use a piecewise function to basically create something that you already know, like the absolute value function. So the parent function for absolute value is f of x equals absolute value of x. But you'll notice here that this second equation that I've got, which is f of x equals x whenever x is greater than or equal to 0, and minus x when x is less than 0, that's a piecewise function, but it's going to look like this. It's going to be a linear equation, y equals x, for values of x that are greater than or equal to 0, okay, and that goes on forever. And it's going to be a value of minus x whenever x is less than 0. And that's going to go off like that. And that looks exactly like our absolute value function. So just wanted to show that to you because that might come up in a quiz or a project that you may have to do. Okay, finally brings us to step functions. And we're going to use only one step function here because this is the one that you get to see in your lesson materials and also this is the only one that you're really quizzed on. We're going to use the greatest integer function. Now, greatest integer function is defined very simply as it's the largest integer that is less than or equal to whatever number is put in for x. So, for example, let's just say I put in the value of 2.7 for x. Okay, what is the first integer or the largest integer that is less than or equal to 2.7? Well, if you said 2, that is correct because 2 is the largest integer less than or equal to 2.7. If I said greatest integer less than or equal to 2.3, the answer would again be 2. So if you notice that for values of 2.7 for x or 2.3 for x, I still get out a y value of 2. Okay, that's important to know. So if you think about that, that will start giving you a shape that looks like a flat or horizontal line. Okay, if I said 2.99, well, that's really close to 3, but it's not 3. So what's the greatest integer that's less than or equal to 2.99? Well, again, the answer is 2. So what you'll notice then is in terms of graphing this, it's going to look like a series of steps. So from 0 to 1, right, any value that I put in between 0 and 1, okay, is going to be 0, right? Because that's the largest integer that's less than or equal to any number between 0 and 1. Once I get to 1, then it all kind of jumps up, right? Because between 1 and 2, then I have nothing but 1 coming out. Same example that I used earlier with the things in the 2's range. Between 2 and 3, everything is comes out as a 2, and so on and so forth. And you can see how this starts going up in steps. Now, it also goes in steps in the negative direction too, because what's the greatest integer that's less than or equal to, let's say, negative 0.5? Well, if you said negative 1, then you're correct. So it takes on a y value of negative 1, and so on and so forth. And it keeps going like both to the right and to the left in this pattern. Now, I wanted to show one more thing, and I'm going to use kind of like a pinkish color. Okay, so remember what we said with absolute value functions. Anything that happens inside the function, okay, if I add something, it shifts everything to the left, and if I subtract something, it moves it all to the right. So let's say I had an x value of, let's say, 1.5. Okay, so if x equals 1.5 and I add 2, that's going to give me 3.5. And what's the greatest integer that's less than or equal to 3.5? Okay, well, the answer to that is 3. So for that example, if I put in a 1.5, I get out a 3. Okay, so it'll give me that pink line there, and then everything else just kind of, goes along, right, with the same pattern. And that would be there, and there, and there, and there. So really what I've done, well, I messed up the last one, but what I've effectively done is I've just taken that whole parent function and then just slid it over by 2 to the left. Okay, so again, the same advice that I would give you with absolute value functions or piecewise functions. Try it out for yourself by creating a table of values. You plug in your x, you do the evaluation to get out your y, and then plot those things and see for yourself. But those are step functions. And also, I'll also say step functions are useful because they describe some real world situations. Like, for example, mailing letters or packages at a post office. Let's use packages, for example. Um, it might be that for something that's between I don't know, like 0 and 2 pounds, you pay $10 to ship it. But then from let's say something more than 10 pounds to 20 pounds, you pay in $8 to ship it. Okay. Um, and with each change of 10 pounds, you pay a completely different amount. So that's actually described by a step function because within a certain range, like let's say like 0 to 10 pounds, you pay whatever that flat rate is. Okay, from 10 to 20, you pay a different rate. Okay, so those are kind of examples of how step functions are used in real life. I hope you have. I'm sorry. I hope you found all that helpful. And if you do have any questions, please contact me through the standard channels. Thank you.